In this video, we're going to take a look at Chapter 15 on oscillations. To start, we're going to talk about simple harmonic motion. And we did talk about this in AP Physics 1, so hopefully some of these terms are a review, such as frequency and period and their relationship with one another. Frequency of an oscillation is the number of times per second that it completes a full cycle. And we use the unit hertz, and that's one oscillation per second, or sometimes we just say hertz is the unit per second. And we know that the time that it takes for one full cycle is the period, and so this gives us the relationship that the period is the reciprocal of the frequency. And we call anything that repeats regularly periodic, and so that gives us this simple harmonic motion, and it is periodic, and it follows the sinusoidal function here. Now this is the function of the position where we have the amplitude as the x sub m, or the x max, times the cosine of omega t plus phi. And we'll describe what each of these are in a moment. So if we picture an object that is oscillating back and forth, so it's moving this way and then it moves back to the right, and it oscillates back and forth in this simple harmonic motion, we can track its position, and we see that it comes out as this cosine wave here. Well, knowing what we know about calculus, we know that the velocity is going to be 0 at the point where we're changing direction, and so our slope of the tangent line down here is 0. And so we can start to picture, well, what is that velocity graph going to look like, knowing what the derivative of cosine is? Well, we know it's just going to be another sine curve with a lot of the same pieces in there, just maybe a little chain rule and some stuff pops out. In that position function, our coefficient, the x sub m, that is our maximum displacement, and we call that the amplitude. And the argument of the cosine is the phase. Now, this is talking about what is inside the cosine function. And we have that constant phi, and we call that the phase angle or the phase constant. We use this phase constant phi in order to adjust our starting point based on t equals 0. So maybe we're not starting at our maximum amplitude. If we're starting our maximum amplitude, then phi is just going to be 0. But say we're starting slightly below our maximum amplitude, then we are going to adjust the phase of the wave by our phase constant. And finally, omega is our angular frequency. From before, we know that the angular frequency is 2 pi divided by the period, or 2 pi times the frequency. Notice the reciprocal relationship between period and frequency. I want you to take a look at these 3 examples down here and notice the differences. In A, we have the same angular frequency but different amplitudes of the 2 waves, where in B, we have the same amplitudes of these 2 waves, but their angular frequencies differ. And then in C, we have the same amplitude and the same angular frequency, but we have a phase angle phi, where we're just shifted off by a negative pi over 4. So the wave is shifted slightly. And we say that those waves are out of phase. Pause the video and take a look at this checkpoint and go over the answers below here. Quick note about velocity. Knowing calculus, we can find the velocity by taking the derivative of the position function. And when we do that, we get this equation here. We get sine instead of cosine, and an omega pops out because of the chain rule. And so what that tells us is that the velocity amplitude is this omega xm. So we take the amplitude times the angular frequency, and that gives us our maximum velocity. Also, it's important to note, when does this happen? The maximum amplitude of the position does not happen at the same point that the maximum amplitude of the velocity happens. And the reason for that is cosine is equal to 1 and sine is equal to 1 at 2 different places. Likewise, we can take another derivative to find the acceleration, and so omega pops out again because of the chain rule, and we see that our maximum is just omega squared times the maximum amplitude, and that's the acceleration amplitude. But we also notice another relationship, that our acceleration versus time function is simply a negative omega squared times our position function. And so we just multiply by negative omega squared, and we have our acceleration. This diagram here depicts a particular wave from position to velocity to acceleration. We can use our calculus to see that all of the correct extrema line up with zeros, and turning points line up with zeros, and so on. And so this gives us this key point here that in simple harmonic motion, the acceleration is proportional to the displacement but opposite in sign, and the two quantities are related by the square of the angular frequency. Take a look at checkpoint 2 here. If we apply Newton's second law, looking at the force of an object in simple harmonic motion is equal to its mass times acceleration, we then end up with this negative m omega squared times x to give us the force. And so essentially it's just multiplying the acceleration by the mass, and that gives us the force. This comes into play with Hooke's law here, in that simple harmonic motion is the motion of a particle when the force acting on it is proportional to the particle's displacement, but in opposite direction. And so that's basically stating what Hooke's law is dealing with the spring or with anything elastic that gives us this restorative force whenever the acceleration is proportional to the displacement, just opposite in direction. A couple other key things here is with angular frequency and the period. Whenever we have something that's oscillating back and forth on a spring, or just obeying Hooke's law in simple harmonic motion, we can actually find its angular frequency just by k, the spring constant, divided by m underneath the square root. And what's significant about this is the amplitude does not determine the frequency. The baby g does not determine the frequency. And so this is a lot of times used to how we find the mass of an object in space, because we can't use a scale because gravity is little to insignificant. And so we can just oscillate something on a spring and determine its mass as long as we know the spring constant and we can measure the angular frequency. Well, likewise, we get the period is just equal to 2 pi times the square root of m over k. Notice it is reciprocated. Take a look here at checkpoint 3. Now, in a spring, in simple harmonic motion, we have energy, and that energy a lot of time is being changed from potential back to kinetic and kinetic back to potential, and in that transition back and forth. And so with the spring, we have 1/2 kx squared. That's old stuff from AP Physics 1. However, we're going to define it a little differently here to say that our potential energy function as a function of time. Yes, this is still true. This is our maximum. But to write it as a function of time, we are going to use that 1/2 kx sub m squared, the amplitude, times cosine squared omega t plus phi. And what did we do here? All we did is, instead of x, we put in the x function as a function of time. So what this does is this allows us to know the potential energy at any given point in time, not just any position. Likewise, we can find the kinetic energy at any given point in time. Knowing that kinetic energy is 1/2 mv squared and we have a velocity function, we can say that it's 1/2 kx squared sine squared of omega t plus phi. Notice you may be asking, where does that k come from? Well, what you end up getting is m times omega squared if you sub in the velocity, and m omega squared is k, looking back at that equation that we have on the last slide. And so if we add these together using our trig identities, sine squared and cosine squared add up to 1, we add the two energies together, and the total energy is just equal to 1/2 kx squared, which is similar. I mean, that's true. We had that back in AP Physics 1, in that when we stretch something on a spring, the energy we put into it is 1/2 kx squared, and that's going to be the total energy of the system when we let go and let it oscillate back and forth. But the significance here is that now we have functions for any given point in time to find the potential energy and to find the kinetic energy, and likewise the total energy, which those two should always and forever add up to 1/2 kx squared. Use that and take a look at checkpoint number 4 here. Something new here that we're going to look at is an angular simple harmonic oscillator. And an example of that is a torsion pendulum. And so this is using the elasticity from a twisting wire. So imagine we have this disc down here that is connected to a wire, and it just rotates slightly back and forth. And because of the elasticity and the tension of the wire, it just oscillates back and forth. But it's not a swinging pendulum. It's not a spring that goes up and down or left and right. It rotates clockwise and counterclockwise, and that is our simple harmonic motion. Well, this acts just like any other simple harmonic motion and took the Hooke's law and all that. However, we do need to apply some other some other constants here and some other quantities based on rotation as opposed to our linear quantities. So we know instead of force we have torque, and instead of Hooke's law saying that F is equal to a negative kx, well, this is torque is equal to a negative kappa theta, where that's just our torsion constant, and theta is our displacement. So this is Hooke's law. It's F equals negative kx. It's just now translated into Greek, tau equals negative kappa theta. And K is our torsion constant, and it obeys Hooke's law. This is just the angular form. And we replace all the linear variables from those previous equations into the angular analogs. And we find that the period is equal to 2 pi. Instead of m over k, it's I over kappa. Remember, what is I? That is the moment of inertia. So the period of oscillation is going to be dependent upon the moment of inertia of this object, whether it's a disk, a sphere, it could be a solid hoop, whatever it is, the moment of inertia does change the period. And with simple harmonic motion comes pendulums and its relation to circular motion. And so in a simple pendulum, we have a bob of mass m that's suspended from an unstretchable and massless spring. So we got to make sure it cannot stretch, because then we have to bring in elastic potential energy. And the string is massless, or at least the mass is insignificant compared to the mass of the bob. And so this bob feels a restoring force of a torque. And that torque, tau, is equal to negative L Fg. Now, this is the force of gravity times sine of theta. And that's theta is the angle from the reference point if this were hanging and not swinging. You can derive all of this based off of using your trig triangle and looking at the torque that it's going to apply. Pretty simple to do, but this is your equation here. Now, we relate this to the moment of inertia by saying that alpha is equal to the negative mgl divided by I times theta. Now, where this comes from is the fact that the sum of the torque is equal to I times alpha, so we have the alpha here and the I there, just relating what we have up top. And instead of Fg, we write it as mg, the force of gravity is a mass times gravity, and L is here, L is here. But the difference is we change from sine theta to theta. And the only reason we can do this is we're making an assumption that in this simple harmonic motion of a pendulum, that the angles are small. And if theta is small, then you can actually approximate the sine theta by just using theta itself. And so we're making that approximation with the assumption that the angles will in fact remain small. And notice the angular acceleration is proportional to the position, but opposite in sign. And so that is obeying our Hooke's law and simple harmonic motion. So just like in linear harmonic motion, in the angular harmonic motion here, we have an angular amplitude that we'll call theta m, and we have an angular frequency. With a pendulum, it looks a little different, but kind of similar in that it's mg L divided by I, the moment of inertia. Now, you might think, looking at this, well, wait a minute, this is dependent upon the mass, whereas the angular frequency on a spring was not dependent upon the mass. But keep in mind here that, yes, there is mass in the numerator, but there's also mass in the denominator, because I is going to be some fraction of mr squared, so that mass will, in fact, cancel, and you find that this is still independent of the mass. But we write it this way just so we can see it in arbitrary terms, so we can have any shape and put in the moment of inertia and let the masses cancel. And likewise, we will have the period, instead of having m over k, we're going to have L over g inside the square root for the period of the pendulum. Now, if we use a physical object as a physical pendulum here, we do find that it has a complicated mass distribution, and we account for that in our I factor here. Our analysis of a physical pendulum is going to be the same, except instead of having the length L, we're going to use a distance h to the center of mass of the object, and I will be particular to this mass distribution. The period then turns into 2 pi times the square root of I over mgh. Remember, h is that distance from the center of mass. And one thing to note here is that a physical pendulum will not show simple harmonic motion if it is pivoted about its center of mass. So we can use this and we can find the moment of inertia of this displaced distribution of mass using our moment of inertia about the center of mass plus the mh squared. And we can also use that previous equation here, equation 1529, and we can solve for baby g, and we can see that with a physical pendulum, we can let it oscillate, and if we take 8 pi squared times L divided by 3 times the period squared, we can solve for baby g. And so this is a way to find the acceleration due to gravity at any given point on the Earth, because it varies slightly by position, or on some unknown planet. So use this, take a look at checkpoint 5. So any simple harmonic motion can be viewed, if we view it at the right angle, it can be viewed as circular motion. And simple harmonic motion is the projection of uniform circular motion on a diameter of the circle in which the circular motion occurs. So imagine something that's moving in a circle. If we're looking at the two dimensions that's moving in a circle in the xy plane, say, and instead of viewing the xy plane, we change our perspective to look exactly down the y-axis. And we see this circular motion, this thing moving in a circle, now just looks like it's oscillating left and right along the x-axis. And because of that translation, we can take any simple harmonic motion, translate into circular motion, and vice versa. And what that does is it gives us these same equations that we've used in the past, of the position, velocity, and acceleration, and we can use those to translate and project onto a circular motion. Now, if we don't have perfect simple harmonic motion, we have what is called damped motion, and that's when an external force reduces the motion of an oscillator. And so an example of that, we could have a spring that is attached to a mast and is attached to this T-piece here that's in some water, and or just some liquid, it doesn't really matter. But either way, that's going to dampen. There's going to be a force that's resisting this motion, and it's going to change the amplitude of the oscillation. And so we can find this damping force by taking negative b times v, where b is the damping constant. That's going to depend on the vein and the viscosity of the fluid. And so think of where this can come into play here is when we're looking at the pistons inside of our engine of, say, a car, motorcycle, whatever it may be. And when those pistons move up and down, and they're going to have some oil in there coating the sides, but there's going to be some viscosity of that oil that's going to dampen the harmonic motion that causes our engine to turn, and then we translate into linear momentum or energy. We use Newton's law, and we get this pretty unique result in that if we look at Newton's second law, mass times acceleration, so that's the second derivative of the position, plus b times the first derivative, which that's just from this equation right here, the dampening force. And so, and then we add in the restoring force of the k times x. If we add all of these together, we end up getting 0, and because the sum of the forces will equal 0 in this situation here. And so the solution of this differential equation, what's unique about this is in fact a differential equation. and it's a second order linear differential equation. And so we don't really know how to solve those yet. You won't learn that in calculus. You'll have to take a course in differential equations in order to learn to solve that. But if we solve that, we get this unique solution here, that the position is equal to the amplitude, the x amplitude, times e to the negative bt divided by 2m times cosine of omega prime t plus phi. And so what's unique is that this exponential gets in here. We get the natural base popping out in here. We're not going to get into the differential equations of why. Just know that this is the equation, and it is kind of unique. And with that, we can find the angular frequency omega prime. Now, the reason it's omega prime is we're dealing with dampening motion here, because without dampening motion, it would just be the square root of k over m. But with the dampening motion, the angular frequency is the square root of the quantity k over m minus b squared divided by 4m squared. If the dampening constant is small, then omega prime is approximately equal to omega. And for small dampening, we can find the mechanical energy by substituting our new equation with the decreasing amplitude just by using this decreasing amplitude. That piece allows for that decrease in amplitude, the e to the negative bt over m. Finally, here we're going to look at forced oscillations and resonance. And forced, or oftentimes we'll call driven, oscillations are subject to a periodic applied force. Think of pushing someone on a swing. You're applying a force periodically to continue that periodic motion or increase the amplitude of that periodic motion. And we can say that the angular frequency we're going to call omega sub d. And the position is then going to turn into this function very similar to what we've had before. It's just omega sub d. The displacement amplitude is a complicated function of omega and omega naught, so the initial omega that we have, because remember, it's going to change here. And the velocity amplitude of the oscillation is greatest when omega d is equal to omega. This condition is called resonance whenever we have this driven motion. And this is also approximately when the displacement amplitude is the largest. Resonance has an important implication for the stability of structures. If we resonate, think of resonating a crystal glass that can shatter. So if the right note is sung near a piece of crystal glass, then it's going to resonate and eventually shatter. We see bridges collapse because of resonance if we don't support them the right way. And because everything has its own resonance frequency, and if we match that, it can then be destructive because it can be driven off into essentially approaching an infinite type of force. And so forced oscillations at resonant frequencies may result in some sort of rupture or collapse.